Hello, welcome back to session 10. I am Shreya, I'm the TA for this course on regression analysis. So, today I'll be solving a few problems based on the concepts discussed during week 10. So, I'll just wait for a couple of more minutes if somebody joins, and then I'll start away. Okay, so I'll just start. Now, before moving on to week 10 lectures, I would like to recap on week 9 and how there I can see there have been doubts related to generalized least squares and how to do it and whatnot. So just a brief recap I'll give. So this method is applicable when you have a model like this and variance of epsilon equal to sigma square v, where v is not necessarily an identity matrix. Okay, so in such cases what we do, we transform this thing into some revised model such that variance of this thing, epsilon star, variance of the errors of the revised model, this becomes sigma square I, and then we apply our OLS concepts on this transformed model. Okay, so if you do remember what we had discussed, so let's say we had this model where variance of epsilon was sigma square v, and then what we would do, we would pre-multiply with some matrix G, then it would become gy plus gx beta plus g epsilon, such that variance of g epsilon would be sigma square I. Okay, now from here variance of g epsilon can be written as g variance of epsilon, that is sigma square v, into g prime. So we would have sigma square gv g prime. Now this quantity is supposed to be I, so that we can apply our OLS concepts over here. So doing that, gv g prime, equating these two, we would get g as V as G inverse G prime inverse or G prime G inverse. Okay, so from here if we try to get beta hat, this is our new x star, this is our new y star. So we would have x star transpose x star inverse. Now see this one, since we have GVG transpose as I, the assumptions for the ordinary least squares are met. So we can just plain and simple use the OLS formula on the transformed matrix, that is x star and y star, and then we would have something like this as our beta estimates, beta GLS estimates. Okay, and if we substitute this thing, x star is gx prime gx inverse gx prime gy, and this one we can write as x transpose g prime g x inverse x prime g transpose gy, and from here g prime g is nothing but v inverse. So we have x transpose v inverse x inverse x transpose v inverse y. So this is only the change in case of generalized least squares. We just add an extra v inverse term here. There have been questions that this was not discussed, but if you go back and see, I did discuss this one. Okay, so the only change that you have to bear in mind is that you have to, in most probably this v is mostly given. So if it is given, then you just need to substitute. Instead of x prime x, you would have x prime v inverse x. So similarly, from these things, if you are asked to calculate the variance of beta hat, then normal OLS would be x sigma square, one second, so normally you would have sigma square x star transpose x star inverse, because these revised things, they satisfy the least square assumptions. So then just substituting, we would have x star is nothing but gx prime gx and then inverse, then we would have x sigma square x transpose, this is inverse. Okay, and he would have sigma square x transpose g transpose gx whole thing inverse. We would have x sigma square x transpose v inverse x whole thing inverse. Okay, so variance of beta GLS would not be sigma square x prime x inverse, but x prime v inverse x inverse. So similarly, if you have been asked to calculate some let's say the sum of squares due to residual, all you have to do is remember what was the OLS counterpart and use the revised model accordingly. So here, if you remember, we had y prime y minus beta hat x prime y. So we'll plain and simple substitute this one, and this one would be y prime is nothing but gy transpose gy minus beta hat GLS gx transpose gy. So we would have and then this is nothing but V inverse. And remember, note these y are the original y's. Okay, so this is how your all formulas will change. SS square, sum of squares due to residuals has changed like this. Similarly, sum of squares due to regression will also change. Total, that will be summation yi minus y bar whole square minus summation due to the residuals. Okay, so accordingly everything will change. The key thing that you need to note is that this concept, there is some y and some x which are transformed to some thing such that the error term has a variance of sigma square I, that is, it satisfies the constant variance assumptions. And then once this is transformed, if you need to derive, you will just substitute here and work out the solutions exactly as we had done for the cases when the assumptions would have been satisfied, and you would land up at a modified equation where you just need to substitute the values to get the answers. Okay, so this was a persistent doubt. I hope now this is much more clear. And next I'll proceed to a brief recap of what was discussed during week 10 lectures. So we did learn the use of dummy variables and how what was the use. It was to model categorical variables. So usually what you have dealt so far with a continuous response, continuous predictors, I'll say. Okay, so the x's would not be categories, or it would be it would just simply be some values. I'm saying values, but this is a very generally I'm saying, okay, not scientifically. So we would have 1.2 something, 3.5 something like this x value. So far we have dealt with x's like this. But if we have to model categorical variables where let's say we have, like the example that was given, we have 3 machines and we are calculating the execution time, let's say is our response y, and if we see or if we assume that for the 3 machines there is a change in the response variable, so then in order to account for that change we might need to introduce categorical variables into our regression model, and the way to do that is by using dummy variables. And also we learned about how to ascertain the number of dummy variables. So it was said that if we have let's say we have a variable machine which has 1 2 3 4 R blocks or categories, then we would have our total dummy variables. Okay, and this would be, we had noted and we'll also note in the problems tomorrow, this would be inclusive of the intercept term. Okay, so if you follow the lectures, this will be clear, but if not, then while doing sums I'll explain what I do mean by this. And then we try to model 2 or 3 different scenarios by the introduction of some interaction term. For example, let's say we have 2 categories A and B, and we are fitting 2 linear regressions in the beginning. So we can write our model as in terms of a single model. We can write it as y equal to beta naught plus beta 1 x plus z into alpha naught plus alpha 1 x, where z equal to 1 if category 1 and 0 if category B. Okay, and then we can model this entire thing and test for different scenarios. All of these were discussed in the lectures, and for example, let's just dissect this entire regression line into these two categories. So for z equal to 1, that is for category 1, we would have a regression like y equal to, just a minute. Yeah, we would have a regression like beta naught plus alpha naught plus beta 1 plus alpha 1 x, and for category B we would have it as y equal to beta naught plus beta 1 x. So let's say this is the line for category B, and we would, for category A, we would have like some different line. Let's say okay, so for, let's say this is the category B line, and for category A it could be something like this. Okay, this is category A, let's say. So then what we are seeing, this intercept let's say is beta naught, and this intercept is beta naught plus alpha naught, and the slope is say beta 1, and the slope for this line is beta 1 plus alpha 1. Okay, so this could be, normally we are assuming that this scenario, if we have to model, then in a single line we can write it like this. Now if the two, I'll just so there could be two situations. So if we write it like this, alpha naught plus beta naught, so the entire model, we'll write it as beta naught plus beta 1 x plus z into alpha naught plus alpha 1 x, and we can write it as beta naught plus z alpha naught plus beta 1 plus z alpha 1 into x. Okay, now if we test alpha naught equal to alpha 1 equal to 0, then the lines would be identical. That is, a single line can fit the entire data. But if not, if we are to look for let's say this is our h naught, alpha 1 equal to 0, then what we mean is that this is category, let's say B, and our category A would be something like this. So the intercepts might differ, because for this one the intercept would be beta naught, but for but for this one so this is category B and this is, let's say, category A. So for category B is in green. Okay, and For category A, we have something different, beta naught plus alpha naught, but the slopes are same. That is beta 1 for the two lines. Similarly, if we test for something alpha not equal to 0, then and if this is true, then it would imply that the intercepts are same. But if alpha 1 not equal to 0 and alpha 2 not equal to 0, then we would have different lines for category A and B. Okay, so the general way is to model our data in this manner. So here, as it was discussed in class, we have two categories. So we will have two dummies, and the first dummy is represented by z0, and the second dummy is represented by z1, where z0 is always 1 and z1 is 1 for category A and z1 is 2 for category B. So we can rewrite this thing entirely as y equal to z0 beta naught plus beta 1 x plus z1 alpha 1 plus alpha 2 x. So if we so now here, if we look carefully and expand this term, we will see that there are, since this is 1, I'm excluding this, consider this one. So here we'll see this xz is the interaction term. Okay, so in this way we can model. It might seem a little confusing. Please go back to the lectures to get more clarity on this, and while we do sums, this thing will become particularly clear. Okay, so this was what was discussed. So finally we'll jump on to the questions. I'll just go back and check if anybody has come or not. Okay, so let's start. So here the first question says that consider fitting a regression model with a continuous variable y equal to beta naught plus beta 1 x1 plus epsilon. If you have to incorporate one categorical variable with three categories, then the number of dummy variables you need to add to the model will be. So the thing is, 3 categories means 3 blocks. So it implies 3 dummies. This is the first thing. Now, next thing what you have to see is that we have something like this. So if you write the X matrix, we have this beta naught. This is always 1. And beta 1 we have x1, x2, similarly xn. Okay, so we can consider this one to be associated with this beta 1 category. It acts like a dummy variable. Okay, so like I mentioned, z0 and z1 in the previous case, z0 is always 1. So similarly, that is the reason. So this column always acts as a dummy variable. Okay, now since you have 3 blocks and you need 3 dummies, one is already accounted for because the intercept term is already present. Okay, so the number of dummy variables you need to add to the model is basically 2, d1 and d2. And if you just take it like this way, d1 is 1, then the combinations of d1 d2 would give you, let's say d1 is 1 if a, 0 otherwise, d2 is 1 if b, 0 otherwise, then d1 d2 combination 1 0 would mean category A, 0 1 would mean category B, and 0 0 would mean category C. Okay, so by the use of two dummy variables, we are able to model this thing. And since we already have this one, 3 blocks means 3 dummies. One is accounted for by the intercept term, so additionally we need to add 2. So the answer is 2. Similarly, now if let's say you have a variable which does not have the intercept term, so then the number of dummy variables that you need to add, 3 blocks, then implies 3 dummies. Okay, so you can add D1, this is 1 if A, D2 is 1 if B, and D3 is 1 if C. Okay, so with these 3 dummy variables you can add. Since in this model the intercept term is not there, you have to use 3 dummies to model this one. So the answer is 3. And this one, let's move on to the next question. Consider the model. Here the first thing you will note is that y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. And we have variables, categorical variable with 2 categories. Okay, so then this implies in total, that is inclusive of intercept, we would have 2 dummies. Okay, but here what they are giving that we are fitting Z1 and Z2. So I'll tell you why we can't fit this model and where the problem will arise, and why we need to drop one of the models, one of the dummies and take the intercept into account. Why we do that and what problem arises if we do not do that. So here if you consider the X matrix, that is, so here you have the intercept term. This is your beta 1, this is beta 2, this is due to Z1, and this is due to Z2. Okay, so this will always be 1. Let's say beta 1, beta 2, you have something x1, x11, x12, x1n, x21, x22, okay, x2n, something you have. And the Z1 and Z2, so for all there are only 2 categories. Okay, so for A, wherever it is A, we would have 1, let's say here, and 0 here otherwise, and wherever we have B, we would have 1 here and 0 otherwise. Now if you look carefully into the first, third and the fourth column, can you see that the first column is actually the sum of third and fourth column? So since there exists a dependency, a linear dependency between these 3 columns, we are being faced with the problem of multicollinearity and perfect multicollinearity, and such so that the rank of this matrix no longer remains a full rank matrix. And so since it is not full rank, we cannot get x prime x inverse and all the problems of multicollinearity. Okay, we just cannot get an inverse, because this one plus this one is equal to this one. There exists a perfect linear dependency. So in order to circumvent this problem, what is usually done is that let's say one of the dummy variables is dropped. Alternatively, the intercept can also be dropped, but usually what is done is that one of the dummy variables is dropped. So the answer is, will it be possible to get LSE estimates if you consider both the dummy variables? The answer is no. The short answer is that there are two categories, so including the intercept variable, only one extra dummy variable can be incorporated, and the reason why we have to do that is this one. Okay, so next I'll proceed to the next sum. Somebody is here, it seems. 1 second. Hello sir, can you see my screen? Okay, I'll assume that you can see my screen, so I'll proceed to the next sum. So here what we have been told that we have to use one dummy variable z to distinguish between two groups. These are the two groups, set A and set B, and we have been asked to use a dummy variable z such that z0 implies set A and z1 implies set B, and then we have been asked to fit this model. Okay, y equal to beta naught plus beta 1 x plus alpha naught z plus alpha 1 x z plus epsilon, and we have been asked to find out the least square estimate of beta 1. Okay, so the thing is how we should go about this problem. So in order to find the estimates of our regression parameters or coefficients, the first thing we have to do is write down the X matrix. Okay, to write it in the form of y equal to x beta plus epsilon. So if I write down the X matrix in this method, how should we write down? So this one is, the first column should correspond to beta naught. So here we have 8 observations, beta naught is there for all of them, so this will have 8 ones, 1 2 3 4 5 6 7 8. Next we have the column corresponding to beta 1. Here we will write x1 x2 from let me just write this as x1 x2 x3 x4. First I'm writing this down, and then I'll write this one, x5 x6 x7 x8. Okay, x5 x6 x7 x8. Then we have the column corresponding to alpha naught, so alpha naught z. Now z equal to 0 when we are taking observations from set A. So the first observations correspond to, okay, I'll just write in figures, that will be more effective, I think. I'll write the actual figures. Okay, so I'll repeat. For beta naught, all would be 1. For beta 1, we'll write whatever x values we have, 18, 10, 22, 12, and then from set B I'm writing 19, 17, 18 and 16. So for alpha naught, we'll write the values of z. So for set A, z is 0. So 0, 0, 0, 0, 1, 1, 1, 1. And for alpha 1, we would write x into z. So x column is this one and z column is this one. So alpha 1 column would be 0 into 18, 0, 0, 0, 0, and again 19, 17, 18, 16. So this is our X matrix, and the beta vector is nothing but these in order: beta naught, beta 1, alpha naught, alpha 1. Now be mindful, if you are changing the order here, then beta would also be written in that order. Let's say if you're writing alpha 1 before alpha naught, I mean if this column comes here, this column comes there, then this one would also change: alpha 1 here, alpha naught here. So there has to be parity such that multiplying x into beta, we can get back to the original equations. Okay, so you have to be very careful about these things. Okay, now once we have the X matrix, and we also know how the Y matrix should look like, so corresponding for 18 we have 51. So same thing we'll write down, and first set A, and then set B 49, 42, 50, 36, whatever we have, that is our Y. So now once we do have our x's and y's, we just need to compute this thing: x prime x inverse and x prime y, where x is nothing but this thing. I'll write it again: 1 1 1 1 1 1 1 1. Then this is 18, those things whatever I wrote here: 18, 10, 12, 22, 12, and so on. So this is beta naught, this is beta 1, this is alpha 1 and alpha 2, whatever we had. We'll just use this x, take x transpose x inverse and then x transpose y, and we would land up at a beta. So if you do the calculation providing all these estimates, you would get, I'll just write down the figures. Please check if you do arrive at this thing or not. So you would get something like this: minus 36.604, 4.813, minus 1.396, and minus 0.113. So this is the estimate of beta naught hat. This is the estimate of beta 1 hat. I mean, this is the estimate of beta naught. This is the estimate of beta 1 designated as beta 1 hat. This is the estimate of alpha 1 designated as alpha 1 hat. And similarly, no, we had alpha naught. So here, my bad, this is alpha naught, and this is alpha 1 hat. Okay, so here we have been asked to find out the LSE of beta 1. So beta 1 LSE is nothing but this one. This is our answer, 4.813. The key to solving these kind of problems is that you just need to write down the design matrix and then apply this formula of beta and take the estimate corresponding to how you have written the design matrix. Okay, proceeding to the next one. So here again, what is the estimate of alpha 1? So here we have seen the last one is alpha 1, because the last column corresponds to alpha 1, which has a coefficient of xz. So this is beta 1 hat, and alpha 1 hat is nothing but coming from the previous alpha 1 hat is minus 0.113. Okay, pretty straightforward. So let's proceed to the next sum. So here we have been asked to consider the data in problem 4. Before that, I'll just ask if anybody is here. Okay, fine. Okay, so here we have been asked to see if a single straight line model fits all data. Okay, to consider the data in problem 4. So the model in problem 4 was that y equals to beta naught plus beta 1 x plus alpha naught z plus alpha 1 xz. So this one we can rewrite as beta naught plus alpha naught z plus beta 1 plus alpha 1 z into x. So to see if a single straight line model can fit all data, this term and this term, sorry, I put it in a wrong manner, just bear with me. This one. So this term and this term should vanish, will only vanish when both are set to 0. Only then this z variable will not have any contribution, and it will the regression lines will not be different for the different sets. So here it has been given what to test h naught, but in exams if it is not given, you need to categorize things together and then you have to check what it implies and how the h naught should be constructed. So here it is given that h naught is alpha naught equal to alpha 1 equal to 0 versus h1 not h naught. So how we should go about this problem? So if you remember, we had our f statistic for extra sum of squares method. We would write it as sum of squares due to residuals from the restricted model minus sum of squares due to residuals from the full model by sum of squares due to residuals, mean squared residuals from the full model, and the numerator would be divided by r, that is the number of restrictions. Okay, so this was the extra sum of squares f statistic to test our hypothesis together. So I'll just I hope you remember this one. I'll just write it once more. This is SS residuals due to the restricted model, that is the model under h naught, minus sum of squares due to residuals in the full model divided by r by ms residuals. Okay, now here first we'll consider the full model, because we have already found, we already have the beta hat estimates. So the beta hat estimates from the full model as we had calculated was this one. Okay, minus 36.604 and what else did we have? Yes, 4.813 minus 1.396 and minus 0.113. So sum of squares due to residuals from the full model would be nothing but y prime y minus beta hat x prime y. So this is y. So this is our beta hat, let me write it as full. Okay, and x was all x was all this one, all 1 in 18, 12 for beta 1, for alpha 1, alpha 2, so alpha naught, alpha 1. So this was our x. We would simply compute, and y was whatever y we had, that one, 51, 8 and so on and so forth. So substituting this y transpose y minus beta hat, that is this beta hat, to x transpose y, we would obtain S is residual to be something around the full model would be 48.124. Please check this, okay? Just substitute y prime y, this is your y, the original y. Beta hat is this one with all estimates of beta naught, beta 1, alpha naught and alpha 1, and then x is this full thing. This is the sum of squares of residuals from the full model. And the full model, as you can see, has 1, 2, 3, 4. So it has 4 unknown parameters. So error df would be n minus 4, and here n is 8, 8 minus 4 is 4. Okay, so from this thing we can write this as the ms residual from the full model also we are getting, that is 48.124 by 4, that is 12.031. Okay, anybody is here? Okay.
Yes, ma'am.
Okay. So from the full model we are getting these three quantities: the sum of squares of residuals due to the full model, the mean squared residuals due to the full model. Now we need to compute the sum of squares due to residuals from the restricted model. How will we do that? So remember, what was our restrictions? Restrictions were, the full model was this one. Full model was y equal to this thing, beta naught plus beta 1 x plus alpha naught z plus alpha 1 xz. So this was the full model for which we had derived the sum of squares due to residuals and the mean square. Now h naught was what? H alpha naught equal to alpha 1 equal to 0. So under h naught the model then becomes y equal to beta naught plus beta naught x plus epsilon. Okay, so under h naught, under the restriction, the revised model becomes this thing due to beta naught and beta 1, that is 1 1 1 1 1 1 1 1, and all the x's that we had, 18, what we had, 18, then 10, 12, 22, 12, and so on and so forth. So under h naught our x matrix will not have 4 columns, because we are taking this into consideration that alpha naught and alpha 1 are 0. So in that case we would have just 2 matrices, and the beta vector would also be beta naught and beta 1, and applying our then beta hat under the restrictive model would be x star inverse x star y, and we would have only 2 estimates of beta naught hat and beta 1 hat, and this would, if you compute, you will get this as minus 36.06 and 4.678. So once you have this beta hat under the restricted model, this is the restricted model, the entire thing. Okay, so under the restricted model, the sum of squares due to residuals under the restricted model would be y prime y minus beta restricted hat transpose x star transpose y. Okay, so in order to find out the sum of squares due to residuals from the restricted model, you need to find out the beta hat for the restricted model, and then just use this formula with the revised model matrix and revised beta hat estimates, and then if you compute this thing, then you would get this as something like 69.08413. Okay, so once you have this, we'll just substitute the values over here. So we have all the values needed that we needed, so we'll just plain and simple substitute all values over here. Okay, so what we had, this one is something we got 69.08413. This one we obtained already as 48.124, and ms was nothing but 48.124 by n minus 4, that is also 4. So if we compute this thing, the value is 0.8711, and the critical point would be an f 0.05, upper 5% cutoff for an f distribution, with the numerator df will be the, oh, okay, sorry, I missed something. We have this, I have written this one and this one. We need to divide by the number of restrictions, that is r equal to 2, because here we are setting alpha not to 0, alpha 1 also to 0. So 2 restrictions. So we have to divide the entire numerator by 2, and then we'll substitute the ms residuals. We would obtain this number, and it should be compared with an f distribution with df 2 and the error df, that is 4. So if you see from this f table, this is the cutoff point alpha, above which 5% of the observations lie. So for f df 1 2 and 4, the cutoff is 6.9. so this critical value is 6.9, and since our f observed, that is this thing, is less than f critical, we will accept h naught. If it would have exceeded, we should have rejected h naught, but since it is less, we will accept h naught, that alpha naught equal to alpha 1 equal to 0. So the answer to this question is that the decision is h naught is accepted. Okay, and quickly I'll just skim through the 2 remaining questions. So do you have any question for this one?
No, ma'am.
Okay, thank you. So the second last question, we have 2 sets of data involving values of x and y, but we are unsure whether to fit the data separately or together. So we fit an 8 parameter model like this, where z is a dummy variable who takes 2 values, 0 for set A, 1 for set B, and the hypothesis is, will a linear model fit all data? So if we rewrite this thing, okay, so we can write this as alpha naught plus z beta naught plus alpha 1 plus z beta 1 x plus alpha 2 plus z beta 2 x square plus alpha 3 plus z beta 3 x cube plus epsilon. Now we want to restrict to linear terms of x. So automatically alpha 2, beta 2, alpha 3, beta 3 are set to 0. And we want to see, will a linear model means a single. Okay, so if a single linear equation is to fit all the data containing data for two categories, then see this z variable that is embedded here and here, this is causing trouble. This is 1 for set B and this is 0 for set A. But if the terms with that, they are also set to 0, then it would be overall, then the contribution of this z term would not matter, and we could fit a single line, that is alpha naught plus alpha 1 x for the entire data. So if this is given, then we need to test the hypothesis beta naught, beta 1, beta 2, beta 3, alpha 2, alpha 3 equal to 0. That is option C. Okay, and the distribution of the test statistic to test this hypothesis is nothing but it's an F distribution. We have to find out the number of restrictions and n minus number of unknown parameters of the unrestricted model. So here we have number of parameters of number of unknown parameters of the full model is 8, because you see we have fitted an 8 parameter model: alpha naught, alpha 1, alpha 2, alpha 3, beta naught, beta 1, beta 2, beta 3. So it's an 8 regression parameters are unknown. So, and the number of restrictions are how many? Beta naught, beta 1, beta 2, beta 3, alpha 2, alpha 3 equal to 0. So here there are 6 restrictions. So our F statistic would be, distribution would be F 6 n minus 8. Okay, where n is the total number of observations. Okay, any doubts, sir?
No, no, no.
Okay, so this was all about this week's session, and we learned how to use dummy variables. What is the number of dummy
Ma'am, how
variables?
can find the slope in this case?
You want to find the slope.
Yes.
So if this is accepted, that a single model can be found, can be fit, then you just need to fit y equal to alpha naught plus alpha 1 x, write the corresponding x matrix, and then get beta hat, and the second estimate that you get, that will be the slope. Okay.
Okay, okay.
Okay. So I'll stop the session today. Thank you for joining. And we discussed how to make use of dummy variables to model differences in responses over different categories. And most importantly, that we have to consider here is that we have to uh, select on the number of dummy variables that should be included in the model, so that we are not faced with problems of multicollinearity. And also we learned how we should incorporate interaction terms and what to test, so that the final course of action that we should take is that first we will uh, at the beginning we will not assume that they are same. We would take a composite some model like this. Okay, we'll just uh, write it in terms of different model variables. So I'll just whatever I'm saying, I'll just put it down. So if we are given a data with some categories, we will just first write down this beta naught plus beta 1 x plus whatever we have plus z1, same thing, plus z2, and this is always 1 if, and the remaining will depend on the number of blocks that we have. So r minus 1 dummies here we'll have, and then first we would fit this, and then we would carry out appropriate tests of whether the slopes are equal, or the intercepts are equal, or the curvatures are equal, and so on. Whichever is satisfied, whichever is true, based on these tests we will finally land up at the final variable, land up at final variable.
Okay.
Okay, so first we will not assume anything, first we'll just fit, and then we'll test various hypotheses, and whichever turns out to be true, or more evidence, whichever has more evidence, we will select that model to take these categorical variables into account. Okay, so this is what we learned in this week. So if you do have further questions, please use the discussion forum, and we'll try to
Ma'am, how
reply.
can find the test when more than two dummy variable, two or more than two dummy variable?
Same thing, only for you have to ask questions whether the first you are assuming that all are separate. Now you will I mean, once you do in practical situations, you have to ask yourself that is the whether one single regression can fit all of the data. Then we just need to test for the significance of the associated uh, with these dummy variables. Okay, but if that is rejected, you see that one model will not be able to fit the entire data. Then you come to its subparts. Are the slopes equal, are the curvatures equal, and then so on. You have to, I mean, based on your objective, you have to devise the hypothesis and then test accordingly. I hope I'm able to answer your
Actually,
query.
ma'am, you have just explained in the previous question where one dummy variables,
Huh.
and then we have to find the delay single model could fit.
Hmm.
In case of when given Z1 and Z2 are
Hmm.
two dummy variable, yeah,
Hmm.
Z1 and Z2, Z3,
Hmm.
three dummy variable.
Hmm.
So we can do the same thing.
Yeah, we can do the same thing. So first is you'll check if at all three lines or are actually needed. Okay, so
Yeah,
here it
yeah.
was that was for two categories. So here, uh, if you have three lines, first you're assuming something like this. Okay, then you could
Yeah.
assume all are parallel. You could
Okay,
assume
okay.
that all intercepts are the same. You could assume something else, that this is different, but their rate of change is same at this point, something like this. Okay, so based on your hypothesis and what you want to find out, and what will be your test, accordingly you have to devise your hypothesis and test the coefficients that you are going to take into account. Similarly, okay, for a two variable situation, it's easier to explain and visualize. For three variables, there could be so many possible things that could happen. So based on that, you have to select. For example, I'll give you a very small example. Suppose you want to consider let's say salaries of let your y variable is a salary of an individual. Okay, and the x variable is a gender, and you want to suppose you are enrolled in a firm which is saying that the starting salary of for both the genders are same. So you want to find out whether this is the case or not. Or somebody says that no, it's entirely the rate of increase is same, but the startings are different. So this could be something like this is parallel, or this is same but the rate is different, something like this. Okay, so based on the question that you would want to address, you would have to test out your hypothesis.
Yes, ma'am.
Okay, so
Mm.
this is just a small example. Okay, then And I'll
Ma'am,
start. Say.
ma'am, any comprehensive practice class after the ending of all the course
Ah,
before the exam?
see, so there are books that has exercises which you can solve, and you can just Google. There are a lot of resources available of solving problems and all. Okay, so
No, actually, ma'am, this is problem solving class. So we got a lot of benefit. Then listen your lecture after
hmm,
very easy to solve the assignments.
hmm,
So I'm
hmm.
just asking before examination session, you will take any such classes for the dot classes or any problem solving classes which is related to examination.
With related to examination, I'm not sure. I don't think there'll be a class that is specifically related to examination, but the discussion forum will be available, and I'll see if it is required, then I may do, but I cannot promise right now.
Okay, okay.
Okay.
Ma'am, so exam में is the same pattern, objective type question or subjective type questions or pen pencil question, which type
Uh,
in the private exam?
I'm not really sure how the exams would be conducted. I'll get back to you. I'll post it in the discussion if I get to know. Okay.
Yes, ma'am. Actually, in the 29th or 30 October, this is final exam. No?
Okay, okay.
So I've first time appearing in this type of exam online in PTL.
Okay, okay,
So I
okay.
have that whether it is pen pencil question or computer based question like the assignment we are submitting regularly.
Okay, okay, okay. I'll ask the authorities and I'll let you know. Okay. Even
Yes, yes.
I haven't sat for this kind of exam, so I don't know. I'll
Okay.
know and I'll let you know.
Okay.
Okay.
Thank you, ma'am.
Thank you. Thank you so much for joining. Have a good
Okay,
day.
thank you.
Bye bye.